Hello, my name's Daniel Huson,
And I'm Mike Steel.
and we would like to help you to get started with CatReNet in this short video.
So CatReNet is a program that allows you to analyze chemical reaction systems. It's of particular interest to people interested in the origin of life and in particular the origin of metabolism. And what we're looking for in a large system is a subset of reactions that in some sense is able to be generated from a food set, but is also autocatalytic.
There are other applications beyond chemistry, for example, in ecology, cultural evolution, and economics. Let's start with a toy example to give you an idea of how you would enter data into the program and what kind of calculations you can do with it. So we're going to look at the task of building a house. So this is not, don't take this literally, this is a toy example. And let's assume that the available materials are wood, metal, sharp stones, and nails. And we're going to follow a number of construction steps. The first couple of steps are going to be about building some tools to make the rest of the construction more easy. So we start off with wood, and using a sharp stone, we fashion a handle out of that piece of wood. Once we have a handle or more than one handles and some metal, we can use a stone to fashion that into a hammer.
Okay, then with the metal and the handle, we can produce with the hammer a saw. And similarly with the wood, and now we have a saw, we can use that saw to cut the wood into planks.
Once we have planks and we use some of the nails that we have available to us, we can build panels using the hammer and the saw as tools. Finally, once we have a set of panels, we can then use a hammer to nail them together to create a house.
So these items at the top are referred to as the food set. They are the things available in the environment. What you see below are reactions. On the left-hand side, you have the reactants, which are combined to produce, on the right-hand side, the products. And the thing that makes that happen are the catalysts. Now, notice that the catalysts are not used up in the reactions, unlike the reactants. They just are undiminished. They make the reaction happen, or at least happen much faster than it would have otherwise.
So this toy example looks like this when you put it into CatReNet input format. So we list the food set, and then we list the reactions R1 to R6 with the reactants mentioned first, and then in brackets we mention the catalysts, and then after the arrow we show the products.
Just one point here. Notice that in reaction 5 we have two catalysts mentioned, hammer and saw. They both have to be present as a catalyst jointly.
With that format in hand, we are ready to paste the data into the CatReNet program. We've entered the input foods set, and now we're inputting reactions 1 to 6. And we're going to run one of the mini algorithms, in this case, the maxCAF algorithm.
So maxCAF is the largest set of reactions that's generated by the food set, and where every catalyst, the first time it's needed in a reaction, it's available, it's already been produced, or it's in the food set. So here we see all 6 reactions form a CAF.
Now we're going to modify our toy example slightly. So rather than having sharp stones as available material, let's pretend that we just have stones available as a material. So before we can go through the construction steps, we need to take a stone and create a sharp stone using a hammer.
Notice, however, that the hammer is not available until later in this process. So that's kind of like a chicken and egg type problem here.
Yeah, and the interpretation here, if you think of catalysts, is that when a catalyst is not present, like we have no hammer, then we can still get to sharp stones, but at a much slower rate. So, for example, we might search through the stones until we find that one that's sufficiently sharp. So taking this slightly modified example, we can produce an input file for CatReNet. Here it is. Now the food set is slightly different. We've got stone rather than sharp stone, and we have 7 reactions. One new reaction takes stones, and using a hammer makes sharp stones. To explore the modified example, we need to put the food set into the top part of the input panel and the 7 reactions, reaction 0 to 6, in the reactions input. Then we go to the algorithms menu and choose a maxCAF algorithm.
So in this case, there is no CAF at all, simply because there's a reaction that has to proceed without catalysis, at least initially. But there's this more flexible notion called a RAF. And in that case, you do allow a reaction to proceed uncatalyzed as long as eventually the catalyst is produced by the system.
This is shown in this visualization. Initially, the reaction that produces sharp stones happens at a low rate because there is no hammer. And once the hammer is produced in this network, you will see that the availability of sharp stones will significantly increase now.
And you see on the left there, a house is about to be produced. It's being catalyzed, and one of the reactants is coming in. The second one is just about to come in now, and now you'll finally have the house being produced.
Yeah, so that gives you some idea of the kind of calculations that you can do with CatReNet and the kind of visualizations that you can look at in the program.
Well, what's next, Daniel?
Well, I would suggest that you folks visit our GitHub page. There you will find more description of the software or the different features that it has, and you can also look at the code itself. And
you can install CatReNet and explore the large number of features.
Yeah, last year we published a paper in bioinformatics where we give a brief introduction to the software, and from that point you can move on to a number of other papers that explore the mathematical foundations of this approach in more detail.
Thanks very much.
Yeah, thank you, and bye-bye.